So earlier we looked at the Reynolds transport theorem and we sort of illustrated the idea behind it by considering Eulerian versus Lagrangian frames of reference. We talked about in one case following a particular particle through time and space and looking at its motion, its velocity as a function of time and its position as a function of time, and we decided that was rather impractical. So we decided to use the control volume approach, which is an Eulerian system. What one does in that system is to look at a particular volume of space and look at the velocities of the particles when they are in that volume. The problem is that we can't apply our standard F equals ma to a volume. It always has to be to a particular mass. And so the Reynolds transport theorem essentially helped us go from the Lagrangian frame of reference to the Eulerian frame. And we said that we could write it for any conserved quantity, whether that's mass, momentum, or energy. So we talked about intensive and extensive quantities and the fact that they are related by a factor of the mass of the system that we are considering. So we'll go ahead and expand on that in the next few minutes. Just for reference, we will write out the fact that when we are considering a particular mass, well, let's start afresh. So when we are considering a particular mass, we can write the equations that conserve the quantities associated with that mass. We could write, for example, conservation of mass to be dm by dt equals 0, where d is the material derivative that essentially signifies the fact that this derivative is being applied to a particular mass. So this is saying that the mass of the system doesn't change with time. That is, mass is neither generated nor destroyed. If I am looking at the momentum of a particular set of particles of fixed identity, I could write dmv by dt is equal to ma, where again I am writing the capital D just to signify that this is for that particular mass at that instant of time. And I could equally well write a conservation law for energy, which would be d m e by dt is the sum of the net heat and work terms acting on the system. I could more generally write this as d of whatever quantity it is that I'm interested in, which I denote by capital B, that we derived in the previous, we just talked about it in the previous video. I'm just going to write it out here as the time rate of change of my quantity plus whatever's coming in or going out through the surface area So this is the total, let's see. This is the total rate of change this is due to the time rate of change, and this is due to whatever is entering or leaving the system through the surface area. So let's go ahead and see how we get that. It's easy enough to do that if one were to go back to vector calculus from, I don't know, your first year in college, but we can work with a simplified model here. Let's look at just a one-dimensional system so that we don't have to worry about all those integrals in 3 dimensions. So let's say we have a particular control mass that occupies a particular control volume at a given time. So I have a control volume and this control volume is fixed in space. So this is my CV, control volume fixed in space and time, and I am looking at velocities in that control volume for my analysis. And let's say that at time t equals 0, there is a certain mass that occupies that control volume. Now I can apply F equals ma to that mass, not to a volume really. So let's look at what happens to the mass that's sitting in that control volume at time t equals 0. So at t equals 0, control mass Cm is coincident with Cv. Right. So I can say at time, let's make that at time t so that we make it more general. So at time t, my system property is the same as my control mass property. So the control volume property rather. So system refers to the control mass. So my B for the system is the same as the B for my control volume. Now let's say at time t equals delta t, that whole mass moves forward with some velocity v. So now my control mass is occupying a slightly different volume in space, and it's given by that. So let me mark this portion as 1. That's the volume that was vacated by the mass as it moved out of the control volume. So the remaining part of the control volume is Cv minus 1. And the part that actually moved out now experienced different conditions, so it's occupying a different volume, maybe 2. And so that's the portion in red is my system at time t plus delta t. So now at time t plus delta t, B system, so that refers to the mass, that is equal to what is in the control volume still. So that's my stuff inside the control volume at t plus delta t minus the part that came out plus the part that now is outside at different conditions and so has a different value. So what I want to do is apply a conservation formula, a law, to my B system at t plus delta t and at t. So I need to get that relation. So if we were talking about mass, we would essentially say that B system at t plus delta t equals the value at time t. If it were momentum, we would say that this change on the left-hand side, be system t plus delta t minus t equals ma, and so on. So if we are generalizing and saying I want to find dB by dt, that is nothing but B system at t plus delta t minus B system at t over delta t, and so that becomes B control volume at t plus delta t minus B control volume at t over delta t plus these extra terms that got generated. Now, if we take the limit as time delta t tends to 0, I could write it in this fashion, where on the left hand side I'm still talking about a particular set of particles, a particular mass, right? So this is my rate of change of B for control mass. But now I'm relating it to what's going on in the control volume. So that's the change in the control volume with respect to time. And these two terms now are the terms, essentially the rate at which stuff coming out is changing and the rate at which stuff leaving the system on the entry portion, how that's changing. So this, you could say, is the rate of B flowing out, and this is the rate of B flowing in through system boundaries. So that's a simplified form of the Reynolds transport theorem, and we'll be using this fairly often. If I were talking about mass, this would look like dm, on my left hand side would be dm by dt. That should be equal to del by del t of my B for the control volume. So my the mass in the control volume would just be integral over the volume rho dV plus the rate at which mass is flowing out the system boundary. So that would be rho 2 A2 times V2 minus rho 1 A1 V1. And I know that mass is conserved, so dm by dt needs to be 0. So I get essentially 0 is del by del t So this would be mass conservation according to the Reynolds transport theorem. So you can see how this principle could be generalized. I would in general write for any quantity capital B, I could write dB dt equals what's going on in the control volume, the time rate of change of small b over the control volume multiplied by the density. That's the time rate, and then whatever is entering or leaving the system through the surface area, so that's a area integral. So this follows from the Gauss divergence theorem that you saw maybe in the first week or so of class. So this is the general form of the Reynolds transport theorem. And this does nothing but reiterate the fact that whatever happens to the control mass, whether it's mass, momentum, or energy, the way it changes can be related to the change in the control volume, so long as we are keeping track of how the control volume conditions themselves are changing, plus whatever is entering or leaving the system as a result of mass flowing out. So the property of the control volume is changing because some mass is taking away a quantity outside and some mass is entering and bringing that quantity in, whether that's momentum or energy. Plus the conditions in the control volume themselves are changing, so we've got to keep track of that. So all three terms combined give you a way of relating what's going on in the control volume to what happened to the control mass itself.